Hello, ladies and gentlemen. Welcome to our high-performance data analytics session. The convergence of HPC, AI, and big data analytics drives high-performance computing to evolve towards HPDA. However, storage performance cannot keep up with the rapid development of computing power. Therefore, HPC demands faster storage with larger capacity. Now, we'd like to invite Mark Nosikoff, lead storage analyst from Hyperion Research, as our first speaker to share his opinions about data-intensive HPC trends. Following Mr. Nosikoff's presentation, you can download the Hyperion Research white paper.
Hi, I'm Mark Nosikoff, Senior Analyst and Lead Storage Analyst with Hyperion Research. Thank you for joining us for today's session. I'll be providing a brief update on the overall HPC market, as well as provide some observations regarding trends with data-intensive HPC. Specifically, I will share market results from 2020 and five-year forecasts associated with on-premises HPC, as well as some insight into cloud utilization. I'll then spend most of our time on data-intensive HPC-associated areas with a focus on data storage. This will include forecasts, trends, challenges, and opportunities. Just a quick note regarding Hyperion Research before getting started. We are an industry analyst and market research firm focused on the worldwide HPC market and associated emerging technologies. There are reports from sample projects available on our website, including a private study performed on behalf of NASA, shared with permission, and an HPC site update from NERSC from our most recent HPC user forum held in May. Now, on with the numbers. Despite impacts from COVID, 2020 turned out to be a growth year, evidenced by a 1.1% growth rate. Growth was almost exclusively driven by the acceptance of the Fugaku machine at the Riken Research Institute in Japan, which occurred in December 2020. This had not been expected to occur until early 2021. Without that acceptance occurring in 2020, the market would have experienced a decline of almost 7%. Looking across the five-year forecast period into 2024, the worldwide on-prem HPC market is expected to grow at an overall compound annual growth rate of 6.8%. Of the five broader market areas making up the forecast, storage is projected to exhibit the highest growth rate with an 8.5% CAGR. The growth in on-prem data storage revenue is projected to culminate in $8 billion of revenue in 2024. Roughly 20% of users' overall spend on-prem HPC infrastructure is for add-on external storage. For every dollar spent on on-prem servers, an additional 40 cents is spent on storage. Turning briefly to HPC in the cloud. Utilization of the cloud for HPC workloads is increasing. Spending for running HPC workloads in the cloud were added to the five on-prem broad market areas. It is projected to account for roughly 16% of the overall HPC market in 2021. To date, it has largely been incremental and complementary to the on-prem HPC investments. Despite some indications that users are beginning to migrate their workloads to the cloud and either defer or forego on-prem purchases in lieu of investing in cloud resources, the on-prem HPC spending is still projected to be greater than 80% of the overall HPC market in 2024. It should be noted that this view of HPC spending in the cloud is what users are paying CSPs for resources to run their jobs in the cloud. It does not include what CSPs are spending to deliver those resources to HPC. Of the users spending on HPC cloud resources, roughly 1/3 of that is spent on storage in the cloud. In 2019, $1.3 billion was spent on cloud storage and is forecast to be almost $3 billion in 2024. Although the growth rate of spending on HPC storage in the cloud is projected to be double that of on-prem HPC storage, on-prem HPC storage is projected to grow more than 60% of HPC spending on storage in 2024. Again, this is what users are spending for cloud storage resources. It does not include what CSPs are spending to deploy storage for HPC utilization. Let's turn now to data-intensive HPC market, and then specifically to storage for data-intensive HPC. First, some definitions and a quick look at our taxonomy for data-intensive HPC, HPDA, and AI. Data-intensive HPC is a term used to broadly describe new and emerging use cases that place extreme I/O demands on what has been traditionally compute-oriented HPC infrastructure. Big data, high-performance data analysis, or HPDA, and AI all fit within this class of HPC workloads. AI is further segmented into machine learning, deep learning, and other methods. AI is oftentimes, but not always, considered a subset of HPDA. In a soon-to-be-published report based on a recent survey of 141 HPC sites representing over 2,000 HPC systems, users were asked what categories of AI they intend to exploit for their research and data analysis. Machine learning and deep learning were the dominant areas. The research results support our recent forecast for users' on-prem investments. In 2021, data-intensive HPC is projected to represent roughly 40% of on-prem spending on HPC technical servers. Of that spending, approximately 40% is expected to be on AI, with AI exhibiting a growth rate more than 4 times that of the overall on-prem server market. Turning to storage in 2024, almost 43% of on-prem spending on HPC is projected to be on storage for data-intensive HPC. Looking at the AI component of data-intensive HPC storage, it is expected to grow at a rate approximately 4 times higher than the overall on-prem HPC storage growth. This is projected to be approximately $1.6 billion for on-prem storage for AI workloads in 2024. So what's driving this phenomenal growth in data-intensive HPC? The factors are wide-ranging. The race to exascale is one element. Governments, regions, and data centers around the world recognize the value leadership class computing resources can provide in terms of ROI and economic growth. This in turn drives subsequent trickle-down near exascale investments from the next tier of research institutions and facilities. Additionally, higher resolution modeling and simulation from traditional HPC applications in the form of surrogate models and other methods are driving demand for larger quantities of data and higher bandwidth to move and process that data. And probably most importantly is the near proliferation of GPU adoption for AI applications. Rollout of new hardware, algorithms, applications, and use cases in machine learning and deep learning will continue to drive interest in HPCs that can provide fast, capable performance for the most aggressive training, inferencing, and decision support tasks. This is being seen prevalently in what can be considered traditional HPC IT data centers. There is strong evidence of increasing HPC enterprise market convergence as competitive forces are driving many commercial entities to integrate their complex business planning and operational requirements with their existing base of data and related data analysis, while pushing more of their business operations into a near real-time environment. These data centers are increasingly finding ways to apply data analytics to extract value from the growing amount of business-related data available to them. They're finding they need to turn to HPC-oriented infrastructure to provide the scale and performance required to fully optimize the value. The market areas adopting HPC-enabled AI techniques are extremely broad and touch most, if not all, market verticals. From aerospace to financial services to the Internet of Things, AI is being widely leveraged to deliver insights to optimize business value for many organizations' varied lines. The areas to date that have delivered the highest commercial return on AI-related investments range from life sciences to automated driving to cybersecurity to smart cities. Varying degrees of AI-related solution maturity have been leveraged for these areas to emerge as the current most economically important AI use cases. Expect more to follow. Despite the success of the referenced use cases, it is still relatively early days for AI adoption, and challenges exist that are hindering wider scale deployment. Let's look at several of the storage-related challenges. Data-intensive workloads have been driving HPC system requirements beyond those of traditional HPC workloads across all elements of HPC system architecture. Demands on storage, in particular, have pushed traditional HPC storage solutions to their limits and are requiring innovation across many fronts. Traditional HPC storage for conventional modeling and simulation typically consists of project, scratch, and archive workloads. AI workloads present a different set of workloads: ingest, data preparation, training, inference, and also archive. Some possess storage attributes like those of traditional HPC workloads, and others drive newer, more aggressive and extreme aspects. HPC and data-intensive workloads also exhibit different I/O profiles. Traditional HPC workloads are typically based on large sequential I/O, while AI workloads demand a mix of large sequential and small random I/O. Metadata management for AI dataset tagging and labeling requires fast, small random I/O. Use cases also drive a variety of durability and resiliency solution needs. Archiving requires extremely cost-effective solutions without nearly as demanding performance requirements. Traditional scratch applications require high performance, with the ability to offload interim results to durable storage to protect against system failures while in the middle of a large modeling or simulation run. AI solutions require a mix of storage needs for both high performance, transient storage, and durable or resilient storage, including a balanced intermix, large block sequential, and small block random I/O profiles. Additionally, data types and access methods drive different requirements for different types of storage systems. Structured and unstructured data employ varying degrees of file, block, and object access methods. Each access method requires its own unique protocol support that traditionally is delivered either by separate, independent, purpose-built systems or separate elements within a single system that may require multiple copies of the data. Last, but certainly not least, cost always presents a challenge. Data is being generated and stored at an exponential rate, driving system capacity requirements up accordingly. This in turn demands more floor space at data centers, either on-prem or in the cloud, and result in higher power and cooling costs. All are critical factors for a data center manager to understand and address when planning the next HPC infrastructure procurements. As with many aspects of life, challenges are typically accompanied by great opportunities. Storage for data-intensive HPC workloads is no exception. With appropriate attention to the requirements presented with each HPDA, AI workload, and use case, storage system architects and vendors can develop innovations to optimize performance and ease of use for the complete HPC system. Specific storage areas, innovation areas to address for the often unstructured data of HPDA workloads and data lake solutions are varied. One area is heterogeneous I/O profiles, providing a single storage architecture with a single file system that can support the application performance needs of both large block sequential aspects, terabytes per second, and small block random access, IOPS, will eliminate the expense of separate systems and simplify the management and support required of the storage administrator. Another area is support for multiple access protocols. Different phases of the AI workflow can often require serving the data via different protocols. Ingest can occur with object-based data using S3, while training is achieved through NFS file access. Other protocols employed throughout an HPDA AI workflow include MPIO, SMB, and HDFS. Supporting multiple protocols within a single system and a single copy of the data that can serve multiple applications can save expense from multiple systems and excess capacity if multiple copies of the data were previously required. Support for various data access frequencies is yet another case. Some data is required frequently and immediately at the highest terabyte per second or IOPS, hot data, while other data, cold data, is accessed much less frequently and has a limited performance requirement. Utilizations of SSDs, HDDs, with the ability to scale both capacity and new technologies as required satisfy this requirement. Cost-effective storage platforms that can reliably and repeatedly deliver the right type of data where and when it's needed should be well received by the HPC community. Lastly, for today's discussion is a high-density efficient design. HPC storage solutions maintain large capacities of data that typically require racks of equipment, large area of floor space, and associated power and cooling. Use of appropriate materials to facilitate heat dissipation and attention to serviceability can contribute to a cost-effective solution that delivers an optimized total cost of ownership. We've covered quite a bit in a short period of time today. The HPC market continues to grow, driven both by new use cases such as HPDA, as well as by market expansion as traditional enterprise IT data centers increasingly adopting HPC infrastructure to support their HPC-enabled AI applications. Growth is being seen across all areas of the HPC market, with storage enjoying the highest on-prem growth rate. Researchers, engineers, and data analysts are all looking to accelerate their time to results. Whether it be scientific discovery, improved product design, or improving business results through better fraud detection, all will benefit from continued advancements in broad HPC investments in general and in data-intensive HPC specifically. Storage will continue to play a critical role in driving these storage innovations. Data-intensive HPC workloads are expected to generate increasing amounts of data and demand higher utilization of that data to deliver the results expected from the promise of HPC-enabled AI techniques. Users with data-intensive workloads would be wise to consider solutions that specifically address the unique needs of HPDA and AI. They can choose from either purpose-built systems developed solely for data-intensive HPC or more general-purpose systems that can satisfy both data-intensive HPC and traditional HPC mod-scene workloads. In either case, users should pay particular attention to the storage system and ensure it can support their specific and possibly unique application requirements. For storage vendors to be successful in the data-intensive HPC market, they need to fully understand and address the demands data-intensive HPC workloads place on the system beyond traditional HPC mod-scene requirements. Hybrid support from multiple perspectives, for example, I/O profile, protocol support, and media type, will need to be provided in an efficient, cost-effective manner to be considered for even the most modest HPC user, let alone the most demanding scientists, researchers, and business analysts. To learn more regarding data-intensive HPC trends, we invite you to download the white paper, either by selecting the link or screening the QR code. You're also welcome to reach out and provide any questions or comments via email as well. Thank you for your time today. Take care and stay safe.
Thank you, Mr. Nosikoff, for your insightful sharing. Don't forget to download the white paper. Now, we all know storage plays a critical role in HPC, but it has become a bottleneck in our system. Next, we'd like to invite Mr. Zhang Wei, Senior Expert of Data Storage Solution Sales Department, to introduce OceanStor Pacific, Huawei's HPDA storage, and its typical applications in energy exploration, scientific research, education, and manufacturing.
Hi everyone, my name is Zhang Wei from Solution Marketing Manager in Massive Data Storage. I have been working in Huawei for over 10 years, from research and development engineer to sales manager, most focused on HPC storage solution. Today, I'm glad to share our thought on next generation high-performance data analytics storage and introduce our flagship distributed storage OceanStor Pacific. As below, HPC exists in many industries such as oil and gas exploration, scientific research, and HPC solutions include computing, storage, network, and other equipment. Due to continuous research and development investment, we have built a full-stack infrastructure solution for HPC. We focused on the development of IT infrastructure and professional services in HPC. By working with our industry partners, we provide various professional solutions for customers in different industries. And today, I'm going to introduce our HPC storage solution. It's no secret that HPC is playing a critical role in our society. It has become an important driving force for social progress. For example, we can use HPC to accelerate drug screening, greatly shorten the research and development period of new medicine. Another example is from genome sequencing. It took 13 years to fully complete the whole genome sequencing at the beginning. But with the help of HPC, we have shortened the time to just 1 day. In recent years, HPC has become even more closely integrated with big data and AI. Data is become more and more important. And we see the trend of HPC enrolling from computing intensive to data intensive. Let's take a look at the HPC market growth rate on the right table. It shows that data intensive HPC market, including HPDA and AI-based HPC, are growing much faster than traditional HPC market. And we found the workload of data-intensive HPC have similar storage requirement. As we can see here, industry get a lot of benefit from using HPDA and AI technology. However, this doesn't come without new challenge. There may be a lot of challenges to storage system. The top 3 challenges we think are as follows. Firstly, the new technology and application dramatically increase data scale, such as testing car, generate 60 TB data per day for autonomous driving. Oil exploration, application upgrade from 2D to 3D mode, data generate 10x than before. Most of the data are so important that they have to be stored over decades. Every growing data scale will bring bigger challenges to HPC infrastructure with uncertain situation on planning and expansion, such as low enough footprint in DC, more complex data lifecycle management, unpredictable scaling and complexity and performance for budget applying. The second challenge comes from supporting hybrid workloads. For traditional application, they often involve multiple processing phases. These phases usually include different IO modes. I'll take oil and gas exploration as an example. Seismic data processing requires high bandwidth, while seismic data interpretation needs high LPS. Normally, 2 different storage systems are required to handle these 2 types of workload. On the other hand, for emerging applications, they cause big growth in diversified computing powers such as GPU, NPU, and FPGA. This further increases the challenges of storage systems, which need to support diversified workload. Certainly, the diversified data protects accessing cost multiple data copying. This process affects the efficiency of HPC. Let's take autonomous driving as an example. The development process involves multiple phases, such as data ingestion, data processing, model training, and simulation. There are diversified data access protocol interfaces are used in this phase. For example, road testing data from S3 protocol, handling by big data with HDFS, and the result data for simulation or training by NFS. Meaning, you have to copy Huawei data to multiple storage systems and waste a lot of time on waiting. But time is very important to the end-to-end development process. We had a lot of complaints from our customers for this situation. We just talked about the challenges faced by HPC C-level. Next, I'll introduce how Huawei Distributed Storage OceanStor Pacific solves this challenge. Firstly, the architecture of OceanStor Pacific is aiming at data lake infrastructure for unstructured data. In design level, we create a new metadata system which can support both file and object, so that one copy of data could be read and written through different access protocols, such as NFS, SMB, HDFS, and S3. In addition to reducing data replication, higher analysis efficiency also comes from OceanStor Pacific supporting for native protocol functions. When we talk about multiple protocols interworking, what we really mean is that there is loss of semantics and performance. You can see in the right table that compared with other vendors, our solution has low gateway and can support advanced functions of different protocols at the same time, such as code function and object multiple copy. Certainly, as we know, a significant increase of data makes management more complex. In a storage system, high bandwidth and high LPS are always like a cake. You can't have it while eating. Different workloads require multiple independent storage systems and begin to spread. OceanStor Pacific Pioneer file system optimizes the processing of I/O metadata and the complexity management, and then optimize the data layout. This design increases the large I/O bandwidth and reduces the I/O delay of small data blocks. In this way, a system supports both bandwidth-intensive and LPS-intensive workloads. The last important point is that we believe high density in HPDA is very important, which will free up space in the data center for the huge growth of data volume. Our high density include two models. The first high density performance load, OceanStor Pacific 9950, a 5U chassis house can support 8 loads with maximum 80 NVMe SD disk. It can provide 160 GB per second and 2 million LPS. The second high-density compressed mode, OceanStor Pacific 9550, a 5U chassis house can support 120 SATA disk. It can support 1.65 GB raw capacity. On the right picture, as you could see, the high performance density load has the best performance density compared to other vendors' products, about 30% higher than the second best one. And the compressed density of the compressed node is 2.7 times than the general purpose high density server solution. Okay, I just introduced the architecture and the highlights of OceanStor Pacific. Next, let's introduce the application and the value of OceanStor Pacific in several typical industry HPC. The first typical industry is autonomous driving. As an important application in the field of AI and 5G, autonomous driving is gradually entering our life. In the process of research and development of autonomous driving, we need to deploy dozens of road vehicles data to collect large amount of data through camera, radar, and other sensors. And we use it to train and simulate autopilot. Because different protocols need to be used to access data in the research and development process, multiple independent storage resource pools need to be built by traditional way. The data is migrated many times in this process, which not only take a long time, but also bring a lot of data redundancy. What benefit can OceanStor Pacific bring? OceanStor Pacific can support the integration and the interworking of NFCs S3, HDFS, and other protocols. One set of storage can support multiple links of data processing, data zero migration, and the processing efficiency is improved by 25%. Storage cost is reduced by 20%. Autonomous driving development process is accelerated, and more intelligent and safer products can be launched quickly. The second typical industry is the energy exploration industry. Since the beginning of this year, oil price has fallen greatly, which has brought a huge impact on the global energy market. Energy enterprises urgently need to accelerate the realization of investment by reducing cost and increasing efficiency. With the increasing popularity of 3D seismic exploration and the refinement exploration grid, the total data complexity of a single exploration project can reach dozens of gigabytes, which bring high room construction and electricity expenditure, and is urgent to reduce TCO. What benefit can OceanStor Pacific bring? OceanStor Pacific series products can achieve a high space utilization rate of more than 93%, save 40% room space, and reduce TCO by more than 30%. By 5U high-density hardware and large EC technology. At the same time, the high-performance Pioneer file system with POSIX and MPI clients can shorten the overall data analysis cycle by 25%. One set of storage can meet storage requirements of different scenarios in the oil and gas exploration industry and reduce customers' cost. The last typical industry is gene sequencing. In the 20th century, we spent more than 10 years and $3 billion to obtain 3 gigabytes human genome data. With the progress and popularization of technology, now you can do gene sequencing for hundreds of dollars and get the sequencing reports in a few hours. At present, a large gene sequencing organization can generate up to 100 gigabytes data every year. Different storage systems are used for different business model data in the sequencing process, which for multiple data islands and access data cross system. This whole process is efficient and the system maintenance is difficult. What benefit can OceanStor Pacific bring for this industry? OceanStor Pacific can enable high-IO and high-complexity data to be stored in different medium by the cost function for hot, warm, and cold data in a set of storage system. At the same time, it supports data free flow in the storage system and the unified management of data throughout the life cycle. As a result, it can improve data access efficiency and reduce the storage cost of massive data. Finally, here is the HPC storage successful storage in genome sequencing. This customer is the World Life Science Research Institute in Japan. Due to insufficient equipment room space, the institute wanted to store 20 gigabytes of data in 3 cabinets. OceanStor Pacific LAN 515 provides high density and large complexity storage. A single cabinet offers more than 1 gigabyte of available complexity. In the end, the institute adopted 17 cabinets to store 20 gigabytes of data, with only 85U space occupied. In this way, the equipment room space is greatly safe and the system performance is improved by 15%. It greatly improves the efficiency of genome sequencing. That's all for today's sharing. Thank you for watching.
After watching Mr. Zhang's presentation, I'm sure you're as surprised as I am to find that HPC has a wide range of applications in so many industries. Next, Let's listen to our customers' voices and see how they use Huawei OceanStor Pacific to solve research challenges. First, welcome Professor Jiang Xingjun from Xi'an Jiaotong University to share his experience.
Hello everyone, welcome to our video. I'm Xingjun Zhang from Xi'an Jiaotong University. Today, I'm going to talk about a trial on promoting data-intensive supercomputing through innovation in storage subsystem architecture. With the rapid development of 5G, cloud, AI, and other technologies, massive amounts of data such as videos and pictures have grown exponentially. This has promoted the HPC industry to evolve from the computing-driven paradigm to data-driven paradigm. The mainstream HPC system architecture in top 500 will support data-intensive application well. With frequent data access, the storage system becomes bottleneck in traditional HPC system. We introduced two cases of data-intensive application in our research. A typical data-intensive application is climate research. And complex Earth system model such as E3SM moves to higher resolution, which requires more grid cells to cover the Earth. Outputting all the data from each grid cell, and the model runs can make more input-output performance key issue. During research, we found that climate applications are usually mixed loads. Another case of data-intensive application in our research is the latency HPC log. In the whole process of information analysis, mixed workload and multiple protocols are usually required. Based on the above cases in our research, we found that the following challenges in the data-intensive applications. The first one is multiple protocol interworking and hybrid workload oriented. Another challenge of data-intensive application is that amount of data processed per unit time is getting larger and larger. In conclusion, large-scale, high-performance storage system is required. So, we introduced OceanStor Pacific to our scientific research, which is a next-generation parallel file system. OceanStor Pacific features innovations in unified metadata architecture, processing of large and small OS, and distributed parallel client. OceanStor Pacific optimizes the latency of the overhead in each phase to achieve both high bandwidth and LPS to accelerate our scientific research. Now, we introduce some optimization methods of OceanStor Pacific. Traditional multi-protocol interworking is implemented based on file or object storage. By contrast, OceanStor Pacific introduced a 3-0 architecture. The file, HDFS, and object protocols are based on a unified unstructured data infrastructure. Without a primary-secondary relationship, those protocols share one copy of metadata and data to leverage the advantages of both file and object protocols. To further improve the parallel access performance, OceanStor Pacific also introduced the Distributed Parallel Client, or DPC. We also cooperated with Huawei to improve the performance of application software by more than 20% through storage computing collaboration. Another subject we cooperated in is DPU. We are studying the scheduling and offloading of heterogeneous compute power and the feasibility of offloading different operators. in order to reduce the data movement and improve the efficiency by offloading some process to DPU. So the conclusion of my speech is as following. Firstly, HPC industry has evolved from the computing-driven paradigm to data-driven paradigm. Secondly, in our research, we found that the performance of traditional storage system is poor due to a large storage scale, the requirement of high performance and high scalability, and the requirement of the multi-protocol interworking. Then we use OceanStor Pacific to accelerate climate research and big data analysis. Finally, we are studying the optimization technology of MPIO and DPC and DPU in cooperation with Huawei to further improve the performance of storage system in HPDA. That's all, and thank you for watching. Have a nice day.
Thank you, Professor Zhang. Finally, I would like to welcome Dr. Yu, data scientist from West China Hospital, to discuss with my colleague about the challenges faced by IT facilities in near real-time WGS analytics and solutions to addressing these challenges. Welcome, Dr. Yu.
Hello, Dr. Yu. Nice to meet you. In this interview, we'll discuss how the full-stack HPDA solution helps perform analysis of the human genome. We all know that human genome analysis is the basis for precision medicine and healthcare big data. Many people have heard about genome analysis, but few know what it actually is. Can you briefly introduce your research and its progress? Thank you for inviting me. Okay, before we start, let's go over our high school biology. There is an important chapter about the central dogma, which mainly concerns how a DNA is transferred into an mRNA and then translated into protein. Let's further break it down. What does a DNA store? Our genetic information. How about protein? Protein is a basic unit of function execution. For example, hemoglobin carries oxygen around the body. So it's easy to infer that the genome of a person, which stores his or her DNAs, determines the character of this person. In medical scenarios, it can be used to determine whether someone has some disease. Put it in a simple way, it gives hints about the possibility of a person having some disease. In real-life application, of course, things aren't that easy because gene doesn't work in a one-to-one relationship. A classic case is sickle cell disease, where the mutation of one DNA turns round red blood cells into sickle in shape. As a result, their ability to carry oxygen weakens. Many chronic diseases are the results of the multi-genetic effect. In other words, they are affected by many gene pairs together. In addition, environment is also an important factor in many cases. So to perform precision medicine, precise diagnosis is a premise. And precise diagnosis must be based on a large collection of information, such as the patient's genome, protein contents in the blood, habits like smoking or drinking, medical history, and so on. Diagnosis is then given based on a comprehensive consideration of all these factors, or in other words, through healthcare big data analytics. It means that we combine environmental information and genetic information to predict whether the patient is prone to having a certain disease, or that the patient already has a certain disease. This is the application of genome in precision medicine and healthcare big data. Thank you, Dr. Yu. According to my understanding, congenital and acquired factors should all be considered to perform precision medicine or healthcare big data analytics. Is that right? Yes, right. That has given us a much better understanding of human genome analysis. We know that the application of new technologies relies on the support of underlying IT infrastructure. Can you tell us some of the IT-related limitations or bottlenecks you have experienced during your research? That's a good question. The rough draft of human genome was completed around 2000 by the Human Genome Project, since which the humankind has entered the post-genome era, with the second-generation sequencing technology available since 2009, we are able to obtain the complete genome of a person by taking sample once. The data size of a person's genome information is about 3 gigabytes. This information is obtained by combining biological and IT technologies. So first of all, we get a blood sample, and then we run the sample in a sequencer. Instead of providing the full length of gene information, the sequencer offers a short section quickly, which covers many areas of the person's genome. However, this doesn't tell doctors the mutations and positions of mutations. Here, algorithms and computing powers kick in. We need to compare the sections provided by the sequencer with the gene panel to determine gene mutations, which is called gene mapping and calling. What we try to figure out is whether the mutation leads to a disease. To sum up, to obtain genome mutation information from a living sample, we need to combine information technologies and biological technologies. For the IT technologies, the results provided by the gene sequencer need to be stored, and the mapping and calling also rely on IT devices. Here, we also face a big challenge. In the past, it takes 24 hours to run the sample and get the mutation result. For some patients, this means life and death. Missing this time window means missing the key moment for intervention, so we need to shorten this time window. Thank you, Dr. Yu. The main problem that human genome analysis is facing is speed. Does that mean that we need to accelerate the analysis to make it applicable to clinical purposes? Yes, absolutely. Okay. Thank you, Dr. Yu. About genome analysis acceleration, are there any success stories? Yes, of course. And that's exactly what we've been doing for the past year. As I mentioned earlier, we were seeking to shorten the 24-hour analysis window. There were 2 aspects that we could work on. The first aspect was storage. The input and output speeds during mapping were crucial to the time window. The second aspect was computing. The computing includes 2 processes. One is mapping, that is comparing gene sequences, and the other one is calling, that is, obtaining the genotype, we can accelerate both of these processes. Let me start with storage. Storage could be accelerated in two ways. We could replace the traditional HDDs with faster SSDs and NVMe SSDs in the PCs. We could also upgrade the storage architecture, which would not only give us more capacity, but also increase the processing speed based on certain network technologies. In PCs, SATA drives provide a maximum speed of 10 or 12 gigabytes per second. An IP network can improve the speed to up to 200 gigabits per second. In terms of improving computing power, a traditional solution is using more computers, which means we need to buy many nodes, and in turn increase the cost. So we chose the GPU approach. It was complicated, and we could not do it by ourselves. So we partnered up with Huawei, who provided storage, and we also partnered with Sailor Gene, who helped us speed up computing with GPUs. In the simple test environment, we use a large capacity storage system from Huawei, with some parallel computing optimization on the GPU. Without any other optimization, we managed to shorten the time window to 24 minutes. In other words, a simple framework replacement shortened the genome analysis from 24 hours to 24 minutes, a giant leap really. But is it enough? We didn't just stop there. We further analyzed the data stream in the algorithm, or the storage I/O stream during computation. Sailor Gene carried out some algorithm optimizations to better leverage the cache and concurrency mechanisms during I/O control. We know that one of the biggest features of scale storage is high concurrency, so we optimized the algorithm accordingly. The second optimization by Huawei was particularly important. Huawei created a new I/O stream in the storage to further slash the time from 24 minutes to an unprecedented 8 minutes. With other solutions, the analysis time is at least 2 hours. We did a groundbreaking 8 minutes with the help of Huawei. Currently, no other institutions can break this record. Truly amazing. Can you tell us more about the role the Huawei storage system played in the time reduction? First of all, Huawei storage improved the per-thread bandwidth from around 1 gigabyte to 2.6 gigabytes. Which is by around 3 times. Secondly, it has some great algorithm optimizations in cold and hot data treatment in the cache mechanism against our I/O model. That enabled the storage to concurrently handle I/Os throughout computation, and thus made the great time reduction a reality. Thank you again for your clear explanation. I believe we've all gained a deeper understanding of the human genome analysis. I just have one more question. Could you share your thoughts on the future development of genome analysis and how you expect the underlying storage as well as the IT infrastructure to support this? Great question. As I mentioned earlier, genes are just one of the causes for a disease. That's why we've seen the term multi-omics more and more these years. It means different data sets described as omes are combined to study life, such as genome, transcriptome, proteome, and so on. In medical scenarios, we use these data sets together with the scan reports and medical history of patients to help us diagnose diseases precisely. The development of genome analysis to multi-omic analysis demands the collection of all kinds of data, which requires the storage to not only support the genome data, but also support image data and relational databases. In other words, the storage system must be multi-talented. In addition, it must support high concurrency because it will be required to handle the data of a large number of patients simultaneously. So the single node performance, as well as the concurrency performance, must improve significantly. So not only should the storage system support multiple protocols at the same time, its performance should also improve continuously to support the increasing requirements of research in the future. Is that right? Yes. And data security and reliability must be ensured no matter in labs or in industrial applications. Right. I believe with the continuous R&D investment, Huawei will develop more reliable and powerful products that will help you in your endeavors.
Thank you, Dr. Yu. This brings us to the end of the session. Thank you for joining.